give us. So Professor Chen received PhD degree in communication engineering from National Taiwan University. He is now with the Department of Electronic Engineering in National Taipei University of Technology, 台北科技大学, where he is now a full professor. His research interests are consumer electronic, multimedia, denoising algorithm, adaptive signal processing theory, adaptive noise control, machine learning, IoT, and interference constellation. This talk today is titled Basic Compensation for Kernel Adaptive Filter Algorithm. Okay, let's give applause to welcome Professor Chen.
Hi everyone. Thank you for Professor Wang's introduction. I'm Min Chen from NTUT, and I'm very glad to share my research result on adaptive filtering algorithm. And I hope you can, through this talk, you can understand what problem I'm dealing with and the main idea I tackle with this problem. Okay. And today's talk, we have about 3 parts. First, I will introduce the idea of nonlinear system identification problem. Then the second part, I will introduce my research outcome on bias compensation kernel linear mean square algorithm, and the other one is bias compensation kernel maximum Fourier entropy algorithm. And finally, we will review the conclusion of this talk and some of my future work. Okay. So first, let me introduce what is system identification task using adaptive filtering algorithm. And as you can see in this figure, we have an unknown system and we have some input. And the output of the unknown system is unobservable because we need to use some measurement system to observe the output. So the only observed output is here. And the system identification problem is we want to use a system to describe the characteristic of the unknown system. And the input is sent by the received data. Okay. And the output of the system y-hat we will measure the difference between the observed output and the estimated output, and we have an error signal. Then we want to find some algorithm to adjust the coefficient or the characteristic of the system so that its output can as close to as the desired signal or even the unobservable output as possible. So this is the system identification problem. And we usually use some adaptive algorithm to identify the unknown system. Okay, and this is our problem. But actually we have some non-ideal effect at measuring block and the censoring block. For example, in the measuring block, we have some noise. We cannot observe the perfect unobservable of the yn in. We cannot observe the unobservable yn in practice case. Okay. So the measurement may introduce some Gaussian noise and even non-Gaussian noise. And even worse, we have some impulse noise. The impulse noise means some the time duration is very short, but the energy is very strong noise, and it will introduce a very large error when we adjust the coefficient of the filter. Okay, and the other one is sensory effect. The sensory effect means the dependent variable, that means the output of the system, will be only partially observed due to sensory. That means for some sample, the value may be saturated by some certain threshold. Okay, by some certain threshold. So we can only observe part of the true result. Okay, and it will introduce some non-ideal effect. And the other one is the missing data at the desired signal. That means some data may be lost. So in that case, we cannot use the error signal to adjust the depth filter. So that's a problem. And also at the sensing system, we will have some ideal effect. We also have some sensory effect. This is due to the saturation. That means the signal will be saturated in some case, and the input data may be mixed as well, just like the measurement block. So the missing data may be missed in the regressor. That means the input data. And in this talk, we are talking about the third one, input noise. The input noise will create some bias coefficient estimate. That means if the sensing system introduce some input noise here, then the input to the unknown system and to the adjust filter are different, so that the error signal cannot measure the real error effectively. So it will introduce another offset. Okay, and in the literature, the researcher use errors in variables to describe such problem. And sometimes we see this term, noisy regressor. That means the input data may be noisy. And two possible solutions to the input noise problem is bias compensation and the total least square algorithm. Okay, and in today's talk, I will introduce how I use bias compensation idea to deal with this problem. Okay, and for the total least square problem, the technique is very old, almost 100 years ago, and this problem considers the least square optimization problem, and the total means when we consider this square problem, we consider both input noise and the measurement noise. So this is called the total least square approach. Okay, and let's see engineering application. Why the input has some noise, and we can see this example. And this is an adaptive interference cancellation system in radio astronomy problem. Assume we have a radio telescope, just like 天文望远镜，天文碟线这种资料。And the telescope want to observe some astronomical source. And in your lab, you will use the reference antenna to do interference cancellation. Why? Because maybe near this telescope, there may be some base station, and it will introduce radio frequency interference, right? So in that case, we cannot observe the real signal, especially when the interference is very strong. So we usually use such architecture called interference cancellation. And the main idea is because the interference ideally is statistically independent from the astronomical source, right? It is very natural because those two sources are totally different. Yeah, so if we can use some reference antenna as input and after some depth filtering, it will estimate the error, the noise received by this telescope, so that we can cancel this out. And because of the statistical property difference between the interference source and the astronomical source, so that approach can work. But as you can see, the size of the telescope and the reference antenna is quite different. So the received interference source will also be different. Therefore, it is possible that the input to the unknown system is different from the input to the adapt system. Okay, so that is one of the source of the input noise, and the other source may be the quantization noise, because the analog signal, if we want to apply it to the system, you need to sample it, right? So that the analog signal could be sampled to discrete digital signal. Okay, so maybe we will introduce some quantization noise, and those operations may introduce the input noise. Okay, so this is our problem. Okay, and such problem has good solution in linear system. For the linear adaptive filtering algorithm, the bias compensation has well developed, but for nonlinear system identification problem, the problem is still undiscovered. So I find this research gap, and I dip into this issue. Okay, so let's see the nonlinear system identification problem first. And as you can see, suppose we have a space C here, and a conventional adaptive filter are linear. That means we estimate the output by using the input vector and the sum coefficient, and they take inner product, so that we can describe the blue line here. So this is linear. But for some situation, if the unobserved output to the input, their relationship are nonlinear like this, then the linear filter cannot describe that. Okay, so generally for any function f of x, if they are not linear, they cannot well described by the linear adaptive filter, right? So the problem now is how do we learn nonlinear structure, and we assume the nonlinear structure is a continuous function. And one particular approach is we assume if there is a parametric model that is output y is a function can be described by a function of g, and the input is x, and the parameter is w here. And we also want this model is so-called universality, 普适性. That means the parametric model should be able to approximate any continuous function. And one of the approaches is neural network. I think many of you have seen such graph in some machine learning or data science course, right? This is the input vector, and we will transfer the input signal to some hidden layer, right? And then combine them together. So the idea here is if we can use some nonlinearly mapping so that the signal can be mapped into higher dimensional space. Then we apply a linear filter to combine the feature, the output of the hidden layer, so that it can describe any nonlinear function if the dimension is high enough, right? So by this approach we could get a universal approximation for sufficient large of n. Okay, so as you can see here, the mapping from the input space to the hidden layer, feature space, can be described by some nonlinear function. And we want the nonlinear function, the nonlinear function can be learned by some method, right? Then we combine the output of the feature space by wi out to get the output, right? Okay, so this is an idea to model the nonlinear function. And why the mapping from the input space to higher dimensional feature space can work? Let's see a simple example here. Assume the input space is two dimensional, U1 and U2, and the feature space has 6 dimensional, x1 to x6, and assume the result is like this. Okay. So if we want to describe some nonlinear system in terms of the input like this, where A1, A2, and to A4 are some constant, right? So it is obviously a nonlinear function with respect to U1 and U2, right? So I think visualize we can assume that for this problem, if the green point and the green point and the blue point is in the original data space, then in this case we cannot use a straight line to separate those two data, right? But if we can map the input space to a higher dimensional feature space, then it is possible we can rewrite the function f in terms of the feature variable x1 to x6, right? So you can see f is identically equal to 0 times x1 plus a3 times x2, right? X2 is here, right? So if we times x2 by a3, then we get a3 times u1 squared. So this is this term, okay? And the other terms you can trace this result. So for this result, you can see the nonlinear function can be represented as a linear combination with the input feature, right? We combine the input feature with weight 0, A3, 0, A4, and so on to generate the nonlinear function. Okay, so again, visually we can assume that by using some approach in the high dimensional feature space, the original nonlinear behavior can be discriminated by a linear function, a straight line here. Okay, so this example can describe the idea why we want to map the input space to a higher dimensional space. Okay, and now we want to know can we learn nonlinear structure using the existing knowledge of linear adaptive filtering. Okay, and this is another approach. We want to fix the nonlinear mapping and use linear filtering like this. Now the problem is how can we find a fixed nonlinear mapping, and the linear filtering part is the coefficient here. Okay, the omega I here. So that the output is a linear combination of the feature space here M is the filter order. Okay, so now the problem is how do we choose the mapping? For example, the mapping could be if the input is denoted as x, then the mapping may be x to I. But how to choose? We need to guarantee the universal approximation. That means we can approximate most or the continuous nonlinear function we are interested in, right? So now I will introduce the kernel method. Okay, and the idea is exactly the same with the one we have mentioned. The original input space here, and we want to map into some feature space F here. Okay, but the mapping, the nonlinear mapping is implicitly. That means we do not explicitly evaluate the mapping. in Chinese 也就是说我们没有把这个对应真正的函数关系呢直接描述出来。因为那个描述是困难的所以有 kernel method 和方法，它就是找一个隐性的方式 implicitly 把它们中间这种非线性的关系描述起来。Okay. So through the kernel method, the universality can be guaranteed. This theory is very tough, and I still try to I still try to understand the detail. Okay, but because we are engineer, we are in engineer college, right? So some theoretical problems are left to the mathematicians. Okay, those are not our work. Okay. So and another problem for the kernel method is that we need to remember all the input data and the coefficient of the mapping. And why I say that? Let's see the kernel least mean square algorithm, and the algorithm needs some approach. First, we need to choose a kernel function, and we also need to choose the step size or the learning rate, and we need to store all the pairs. Here, alpha I is the expansion coefficient, and xi is the input vector. Okay, and for this problem, we don't have any regularization, and the computation complexity is not high for each iteration. So initially, the expansion coefficient is set here because at this time we don't have error now. Okay, so for the left iteration, we first input the current data xn, n denotes time. So at the time instance n, the output can be described by this function. Okay, xn is the input, and it will take kernel treatment with the data you have sampled, and sometimes we call it a dictionary. We need to store all the input data. That means the dictionary size will be increasing with time. Okay, and the output is linear combination with the expansion coefficient A here. So after we get the output of the adapt filter, and we see the difference between the desired signal and the estimated output. Okay, and the error signal would be stored as well to serve the expansion coefficient for KLMS algorithm. Okay, so by using this model, the main disadvantage is we need to store the expansion coefficient and the input vector forever. So of course, in practical, it cannot work, right? So let's see the idea of that approach. If we want to